Hello, good evening, everyone, and welcome to the latest installment of the SLAC Public Lectures. Probably many of you saw in the news that SLAC has passed a very important milestone. Well, actually, in the winter, but it comes to fruition very recently. We've built a ginormous camera for an astronomical purpose. It's now sitting on top of a mountain in Chile, and it's going to map the whole southern sky. And in this series, we will have a number of lectures about the science that comes out of this project. This telescope will take petabytes of astronomical data, and we're expecting a lot of fascinating things that we're going to learn from this data. But we thought the construction of the camera is such an enormous project and actually a real event, we should have a talk about that. So we're very lucky this evening to have one of the lead engineers on the project, Travis Lange, who's going to tell us how they built this thing, what it is, how big it is, and also how hard it was to put together. Travis is from Minnesota. He got his graduate degree from the University of Minnesota. He then spent a lot of time out here in California at the Lawrence Livermore Laboratory. He was one of the engineers who designed the National Ignition Facility, the NIF, at Livermore. I don't know if you know what that is. That's a facility that basically directs multiple laser beams to hit small pellets of tritium and do controlled fusion energy generation. If you remember the planet-destroying lasers in Star Wars, that's what it looks like. After that project was completed in 2014, Travis came here to SLAC, where he became the lead for integration and testing for this camera, really one of the people deeply involved in putting the whole thing together. And so he's going to describe that experience this evening, and I hope you enjoy it. So Travis, you're on.
All right. Thanks, Michael. I guess I'm gonna just do a quick mic check because I didn't do that before. I probably should have done that. Okay, sounds like it's good and audible. Okay, so thank you for the introduction. Welcome to everybody. It's great to see so many people here. I see a lot of new faces. I see some colleagues, see some neighbors, some friends, and of course my family down here in the front. I'm really excited to show all of you about this LSST camera, world's largest camera, largest digital camera, how we put it together. I'm going to talk a little bit about the Vera Rubin Observatory and the purpose of the Vera Rubin Observatory, and also, how that purpose affected the design for both the telescope as well as the camera. And then we'll go into some pictures that show you how we put the camera together. And then we're going to wrap everything up by showing you some of the images that we released publicly about 6 weeks ago. All right. So we're going to got a pretty good intro from Michael on who I am. So I'm a mechanical engineer here at SLAC. I came here 11 years ago. I was hired as the lead engineer for integration of the LSST camera. In general, I would say that I love these big science projects and I love building things. So this is a great project to have been working on. There's a couple other pictures I threw up here. There's one on the left here is when I was in university, I was the project manager for the solar vehicle project. I don't know if anybody in here has ever been involved in one of these university auto projects, but they're a really good way to get experience. The reason I have this particular picture here, because this is at the Indianapolis Motor Speedway. I get to brag a little bit and say that I have actually raced on the Indianapolis Motor Speedway at 55 miles an hour. So not exactly at super high speeds. The picture on the right is, he mentioned the National Ignition Facility. This is actually the world's most energetic high power laser. The part that I spent most of my time working on is adding a short pulse laser as a diagnostic for that main beam. The picture is actually inside of a very large vacuum chamber. So it's a humongous vacuum chamber. You can see a whole bunch of optics in there. There's one that shows some rainbow colors. That's because it's a diffraction grating that's separating out all the colors into the rainbow. All right, so enough about me. All right, so raise your hand if you've ever been someplace really dark, maybe the mountains of the desert, and you've had the opportunity to see a sky that looks a little bit like this, right? So, all right, keep them raised if you've ever tried counting. 1, 2, 3, 1 billion, 1 billion, 2. Okay, so you're not able to do that. It's something that's beyond our capability. Our eyes can't see it well enough. You actually literally can't count that high, even if you were just counting. It would take more than your lifetime. And then we can't see everything. So we use aids, and the aids that we use are telescopes, right? So that helps us to see things that are more faint and distant in the sky. There's a couple pictures up here of the kind of brief history of observations. The picture on the left is the telescope that Galileo made. So this is the early 1600s. It's kind of the start of what we consider our modern era of astronomy. So before this, of course, people have been looking up at the night sky for as long as people have been around. But the start of using a tool to really improve what we can see in the sky started in the early 1600s. So Kepler and his laws of planetary motion and Galileo with his much improved telescope are what really got started in this process. Picture in the middle is Edwin Hubble. That's him working on the big telescope at the Mount Wilson Observatory outside of Pasadena. So a couple things that he's really known for. One is he was the first person to observe that there's stuff outside of our galaxy. Up until that point, it was assumed that it was just kind of a universal blob of stars. And he really discovered that we have a galaxy, and then there's stuff beyond that. The other thing that he's most famous for is for recognizing that the universe is actually expanding. So things are all universal, they're moving away from us in all directions. So the universe is expanding. In the 1970s, Vera Rubin, maybe that's a name you've maybe heard of already. She did some observations that, she couldn't understand why certain galaxies weren't just flying apart, right? So they're spinning, these things should really be flying apart, and they weren't. They're kind of sticking together, so there must be some cosmic glue that's holding everything together. The only forces in astronomy that we know of is gravity, right? So the force of gravity. In order to have gravity, you need a bunch of mass. So you have to have some matter, right? You need some matter that creates that gravity. And we can't see it. It doesn't reflect light, it doesn't emit light. And so she coined it as dark matter. So that's one term that we can talk about. The other thing that happened in the late 1990s, there were a couple different teams of scientists who were doing some observations of supernova and discovered that not only is the universe expanding, but the rate at which it's expanding is actually accelerating, which is completely in contradiction to the dark matter, because the dark matter should make the universe collapse. And now observationally, we're seeing that the universe is actually expanding, it's accelerating its expansion. We don't understand those things very well. There are a couple of mysteries for us. So what if we could, explain that dark energy and dark matter and the accelerating expansion of the universe? And at the same time that we're doing all that, we could actually map the solar system and the Milky Way, our cosmic backyard, as it were. And while we're doing that, we're going to see all kinds of things that are happening in real time in our sky. So that's actually the goal of the Vera Rubin Observatory. So I think Michael mentioned it a little bit, that the observatory is going to take these repeated images. It's going to take very large field of view images over and over and over across the entire sky. It's going to map everything that you can see, like literally everything that can be seen. The southern hemisphere, not northern hemisphere, but everything that can be seen. And with that, you can make this vast three-dimensional movie of the universe, a time-lapse movie, if you will. And that will reveal, the evolving structure of the universe and capture all the things that are changing over time. We call that movie the Legacy Survey of Space and Time, or LSST. All right, so how are we going to actually accomplish this? So there's three main objectives. It's to have a wide field of view, have everything be very fast, and we want the ability to see very deep, right? So we want to see those really faint, distant objects. And when we talk about the wide field of view, the camera, there's a picture up here. It's a simulated image, of course, not a real image, but each of those little squares is one of the sensors in the LSST camera. There are 201 of those squares in that image. So that's the full array of sensors for the LSST camera. It's big. It's nearly 10 square degrees of sky. So 10 square degrees of sky doesn't mean a whole lot, but I think a lot of people have probably seen pictures of the Hubble from the Hubble telescope. Now, Hubble and Rubin have some different science goals, but when it comes to a comparison of field of view, this is about 5,000 times bigger than the field of view of the Hubble telescope, just to kind of give you a sense of scale. The other thing is those full moons that are transposed on the surface of that image. You can fit like 49 of them. Hubble, you can fit 1/12 of a full moon in a full field of view. We need everything to be fast. So why do we need things to be fast? Well, we're trying to cover all of the sky, and there's a lot of sky, right? If you go horizon to horizon in both directions, it's a lot of sky. So the telescope moves really fast. It can move up to 7 degrees per second. This whole thing has to move really fast. But if we want to move really fast and then stop and take an image, we don't want that structure to then kind of do this for 5 minutes and then wait until it settles down before we can take another image. So the structure of the telescope is very compact. Because the structure is very compact, the optics have to focus the light very fast too. So we call that fast focusing optics. If there's any camera nerds here, it's an f1.2. And then the speed of the camera readout as well. So we have 3,200 megapixels or 3.2 gigapixels of data in the camera. And all of that has to come out really quickly. We are able to read that out in just a little over 2 seconds. And then, of course, that doesn't do us much good unless we actually have it someplace we can do some analysis on it, and then we can access that data. So by the time the shutter on the camera closes, it takes a little over 2 seconds for the data to get out of the camera. And then it takes a few seconds for that data to get from Chile all the way to here at the US data facility here at SLAC. And then another couple seconds for it to be ingested into the servers. So it takes less than 10 seconds between the data being captured and the shutter closing until all that data is here at SLAC. All right, and when it comes to seeing those faint objects, the deep stuff, the bigger the mirror, the better, right? So we want a nice large mirror. This mirror on this telescope is 8.4 meters, nearly 28 feet. And then we need sensors on the camera that are capable of seeing those faint objects as well. One of the aspects of those custom CCDs is that we need them to have very low electrical noise. So electrical noise, if anybody is not familiar with anybody, try to use your phone, take a picture at night. If you try to do that, you're going to get this very grainy, kind of staticky image. That is actually the challenge is the phone can't interpret the difference between the light that's coming into the CCD or the electrical noise that is being that's randomly happening inside your camera. So that is what we call electrical noise. Of course, we don't want that. We want to see a few photons, and we want to know that it's a few photons from the sky and not electrical noise. So we'll talk about how that impacts the camera when we get to the camera. All right. So the picture of the telescope here, we're going to talk a little bit about the telescope. So the picture on the left here, just to give you a sense of scale, there's a couple trucks on the bottom of that image. So it's a large facility. On the top right is the dome for the observatory. That is roughly a 600-ton structure that has to rotate almost as fast as the telescope. Picture on the right is actually inside that dome. That's a fairly old picture. Kevin, you probably took this. This part in the middle, that round circle, is it's like a little over 30 feet in diameter, just to kind of give you a sense of scale. That structure weighs about 250 tons. So that's that 250-ton structure. It holds the mirrors for the observatory, and it also holds the camera. And that's the part that has to slew around at 7 degrees per second. All right, so let's discuss how the wide, fast, and deep impacts the design of this thing. This is a little graphic that shows the light coming in from the night sky. It's hitting this primary mirror. It bounces up to a secondary mirror, down to the third mirror, which is actually part of the first one, and then up into the camera's lenses. So there's three things about this that I'd like you to take away from it. So first is the telescope itself has 3 mirrors, and the camera has 3 lenses. The mirrors are actually providing all the focusing. So the camera by itself would take a very out of focus image. We actually need the rest of the telescope mirrors in order to take an in focus image. The other thing I'd point out is as it bounces off of the secondary mirror, you can see how the beam comes right around the camera. That means that the camera design has to be very self-contained. It can't have anything that sticks out to the side because it would block beam. So we don't want that either. All right. So here's a little video that shows the speed at which, this is a real video, obviously. This is in real time. This is not sped up. That's that massive structure. It weighs about 250 tons, spinning around. I think this is maybe 40% speed. This is before we actually had glass mirrors on it, so there's just a steel mirrors. You can see people walking around on the sides, just to kind of give you a sense of how fast this thing actually moves. All right, so I mentioned that, why not have a bigger mirror, right? So we have this big mirror. It's like 28 feet in diameter. In this picture, you can actually see the 2 different segments, the 2 different parts, right? That primary mirror and the third mirror. So there's 2 different shapes within one structure. It's a really unique design. So it turns out that in order to get the thing from the port and the coast up to the mountaintop, we have to go through a tunnel. So the design for the size of the mirror is literally limited by the Buclaro tunnel that we had to drive through, right? So this road is about 50 kilometers from the town up to the turnoff where we go on our private property. And actually, this is closed for quite some time, like a day, while this mirror was shuttled up this quite busy highway. And we had to close the highway from all traffic in order to get the mirror from the coast up to our property. All right, so let's talk about the world's biggest camera. We'll kind of go through this a little bit like we did the telescope. So this was started in 2015 is when we actually started the LSST camera project. So it's been 10 years now. The resolution, as we mentioned, 3,200 megapixels. The camera weighs like 6,600 pounds. So it's a beast of a camera. It's definitely not going to fit into your phone. And it's nearly 15 feet long. The primary lens, the entrance lens to the camera is over 5 feet in diameter. It's the world's largest lens. And the size of the array of sensors is nearly 25 inches across. So all of those things are actually Guinness World Records. So the lens, Guinness World Record. Array of sensors, Guinness World Record. Completed camera, Guinness World Record. We actually have the one for the camera here. All right. So this is that same CAD rendering. I'm gonna blow up the camera so we can talk a little bit about some of the components. So we got this nice magic CAD design here. So the first thing we have, the primary thing that this whole camera is for, is the CCDs, charged coupled devices. So the CCDs are what converts the photons of light coming from stars into electrons that we can use in our electronics to recreate a digital image. So that's what those are doing. We need to keep those things nice and clean. They have to be super clean because any little dust speck on that surface is going to block the photons of light. So we don't want to have anything on the surface of those CCDs. Those CCDs are in turn mounted on an assembly. I'll show you in a little bit what it looks like. So we call that thing the Raft Tower module. There's 9 CCDs plus all of their readout electronics all in one assembly. There's also, and there's 21 of those. And then there are 4 of these corner Raft Tower modules that have some wavefront sensing, and that allows us to do the focusing for the entire observatory. Those things go into a cryostat. So the cryostat is needed. So you recall I mentioned about electrical noise. So the way that we handle electrical noise of these CCDs is to keep them very cold. We run them at -100 Celsius. And if you run something, if something is at -100 Celsius, and if you do that in air, you're immediately going to have the water vapor in your air freeze out on the surface, right? So we have to put those inside of a chamber and remove all of the air molecules. So you have to take out all the air molecules from inside the chamber. So we have this cryostat where we evacuate it. This thing, and the cryostat it's like 3.5 feet in diameter, about 3.5 feet tall. So it's a pretty big beastly thing. We close off the front part of the cryostat. Now this is both a vacuum seal as well as the final optic. So it's the 3rd lens in the series. We have a whole bunch of electronics. We have all the power supplies, the data acquisition, the networking, all that kind of stuff exists in this utility trunk. On board the camera, we can carry 5 optical filters. Now, an optical filter is something that allows light only in a very specific wavelength. We want to be able to look at different cosmologic phenomena that happen in different wavelengths. And colors also help us to determine distance when we're looking at stars and galaxies. So we have the capability of having 5 optical filters inside the camera. We actually have a total of 6. So we have to have the ability to take one out and put one back in. But at any given time, there are 5 on board the camera. The camera body is the main structure that supports everything about the camera. We have a filter exchange system. So we have those big filters, and we have to be able to switch the colors at any given time. So there's a mechanism that can grab one of those filters and put it in front of the CCDs. Of course, every camera has to have a shutter. Ours is quite large. And we have that large lens that I already mentioned, the L1, L2 lens assembly. This was not an easy thing. It was not all done here at SLAC. It was all assembled here at SLAC. But a lot of the hardware was designed and built here at SLAC. So the utility trunk, the cryostat, the corner raft, the camera body, the shutter, all of those components were actually designed and built right here at SLAC. However, we had help to do a lot of things. So Brookhaven National Lab, they're out in Long Island. They're another one of the Department of Energy national laboratories. They did the design and construction of the Raft Tower modules. So there's the 21 of those Raft Tower modules they supplied. Lawrence Livermore, my former home. Actually, fun fact, the filter assemblies are the first thing I designed when I was still working at Lawrence Livermore. So I actually started working on this before I came to SLAC. So they actually provided all the optics for the camera. And not to be left out, our partners in France, we have there's a whole consortium of national laboratories in France, and they built the entire filter exchange system for us. All right, so now we get the fun part. This is the how we put the camera together pictures. So I'm trying to keep this short, but I could go for hours on this stuff. So apologies if I go long. The first thing that we talk about with the camera is the sensors. I mean, that's really the lifeblood. These are the eyes for the camera. And so we have this Raft Tower module. This is one of those Raft Tower modules. This is about 2 feet tall. It's about 5 feet square or 5 inches square on the bottom. I'll hold it up so you can see the sensors on the bottom. Now this one is non-functional. So these are just sensors that don't work. So this was just a mechanical dummy for us to play with and to take a look at. One of the things that I would like, you can take a look at is you see the lines that separate out the nine different CCDs. Oops, sorry, try not to bump the microphone. The 9 different CCDs on here. My guess is you probably cannot see the gap between those CCDs. I'm just gonna say you can. What is the challenge of installing these into the camera is that, we have to put one of these into the cryostat. You can see on the left side of this right image here, there's on the left-hand side, there is one of those assemblies is already installed. It's actually installed into the cryostat. The right part is us in the process of installing the next one that's right next to it, the adjacent one. The clearance is the same as the clearance you were not able to see on those 9 CCDs, right? This is, it's about 500 microns of clearance between those sensors. So that is about the width of 5 hairs. Your hairs, not mine. Okay, so the challenge is that the biggest challenge, and these are very expensive. These are custom CCDs. They're made specifically for this project. Damaging them is a really bad thing. So each of those raft tower modules was about $2.5 million of components when it was assembled. Damaging the sensors in the process of just installing them would have been a really bad thing. One thing you can see is you can't support it from the bottom. You can't support it on the CCDs. So the only way that we can actually attach to this thing to lift it into place is back here on the backside. So we actually had some brackets and a big old shaft that we used to lift it up into place. So I'm going to show you a little picture quick. We mentioned we had just that cryostat assembly. So we did all that work, all the work of installing the CCDs when it was just a bare cryostat assembly. So this is a picture CAD representation because I can show you things that I can't show you in real life because I can do little cross sections. But you can see a big long, it says the integration arm. It comes down through the middle of that. So that arm is a little bit over 1 meter long. That's a little bit more than 1/2 meter. So I have a 1.5 meter long pendulum. So a 5 foot long pendulum. And at the bottom of that 5 foot long pendulum, I have 5 hair widths of clearance that I have to make sure I don't collide with the adjacent sensors. So that is not an easy thing to do with a long pendulum like that. So I don't know, anybody ever played the kids' game of Operation? Yeah, so some of the older folks maybe remember this game. You try to pick out the bone from the thing and don't have it buzz on you. Well, so this is like the ultimate game of Operation, except you don't get the buzz, you break millions of dollars in sensors. So in order to do that, we had to make a whole bunch of precision stuff. So the picture here shows this very custom-made stage that would travel up and down really accurately. And then also we had the ability to change the position forward and backward, left and right, and do a little rotation as well. And then after we got the rafts partway installed, we actually put a series of cameras looking up at the 4 corners of the raft being installed. And that was so we could monitor all the corners to make sure we weren't going to collide with anything as we were going into the last couple inches of travel. The glory shot on the right hand side. So this is when the last science raft was installed in the beginning of 2020. So it's more than 5.5 years ago at this point. I guess I will say that we did not install all 21 science rafts at one time. We actually put in about 9. We closed everything up. We tested it for several months to make sure that everything was functioning as we expected. We opened it back up. We put in the rest of the sensors, and then we were able to close it back up and do a whole several more months of testing. But the thing is, we're not trying to just take pretty pictures. We're trying to do science with this thing. And to do science, you actually need some precision. So precision in this case, I mentioned the fast focusing optics. So the fast focusing optics, the way that impacts the design here is that if the light is coming into the sensor, if the sensor array is like this, if the light is coming into that sensor array and one sensor is slightly further back or slightly in front, it's going to be out of focus because of that fast focusing beam. And so we needed to make sure that every single part of all the sensors were on the same plane. And we were able to do that. We measured it to 4 microns across the entire 25 inches. 4 microns may not mean a whole lot to some people, but it's a very small number. Again, your hair, not mine. You can take a hair and you slice it vertically or along the length of it into 20 equal pieces. And it would be the thickness of one of those 20 equal pieces. That's the flatness of the entire array of CCDs. All of these CCDs have a lot of wires that we have to deal with. There's over 2,000 power wires. There's like another 500 data wires. There's a whole bunch of telemetry for things like temperature monitoring. All that stuff had to get out of that cryostat. So the cryostat is the vacuum, right? There's no air in there, but we don't live in a place that has no air. We live in a place that has air. So we have to get them between the vacuum and the air. So there's lots of managing of cables. That's really important because any little short or any broken wire, and you might have a whole bunch of sensors that no longer work. So we had to do a whole bunch of testing, make sure all these things are restrained well. Picture on the right is showing that same cryostat. So this is, sorry, I didn't explain. This is actually the back side of the cryostat, so the opposite side from the sensors. So a big plate goes on here to seal that up eventually. And the picture on the right-hand side is that same cryostat, except now it's rotated on its side, and we're marrying up that utility truck that has all of those electronics inside of it. Again, lots of cables, lots of ducting, all had to be managed really well. Once we put that together, we actually put it back on the same support stand and ran it through a whole suite of tests again. We wanted to make sure that after we integrated with all those electronics, it still was working the way it's supposed to. Once we had done that, we were satisfied that all the sensors are working as they should have been. We need to take that cryostat assembly, cryostat and utility trunk, that are all together now, and integrate it with the camera body. So that's the picture on the right-hand side. Now it's that same cryostat assembly, except it's coming at us. You can see the different sensors in that picture. So it's coming through the opening of the camera body into the camera body. So we have this very large lens, right? The world's largest lens. It's actually 2 lenses coupled together in a carbon fiber structure. And we need to get that from this state, which is how we received it from our shipping from Livermore, onto the camera. In order to do that, we had to rotate it 90 degrees. The picture in the middle is actually the process of landing it onto the camera body. There's 6 different legs, this hexapod structure, these 6 different legs that had to be mounted to the camera. The picture on the right shows that after it was all together, you can see the 6 different legs that support the lens structure, lens assembly. And then you can also see at the top of that image is that 3rd lens, or the vacuum barrier to the cryostat. And the space in between is where we put the shutter and that filter exchange system. So that's what has to fit in those last 2 spaces. But of course, those 6 bars that are supporting the lens assembly are a bit of a complicating factor. All right, so the shutter mechanism is a little video showing how the shutter works. It's a really unique design for how the shutter works. There's 2 blades, because imagine they can't go outside that diameter of the camera. So it's 2 blades stacked on top of one another, and they travel at different speeds, so that they eventually close off the entire opening to the focal array. I mentioned the challenge with the struts that support the lens assembly. In order to install the shutter in that volume, we have to go around those struts, and that's a huge challenge. So we've got this crazy contraption. I will say it's crazy. It's definitely a crazy contraption. It actually has 5 different motors to actuate this thing in 5 different degrees of motion. And in order to actually install it, it takes about a sequence of 10 different moves. So 10 different moves, 5 different axes, in order to thread it through those carbon fiber struts of the lens assembly. So the last thing is the filter exchange system. The picture in the middle is actually inspecting one of those filters. So this is looking at, I think it's the R-band filter. So it's, maybe it's G, I can't tell. So this is one of those mirrors, one of those filter assemblies that lets one color of light through, and all the rest of the light is reflected back into our eyes. So that's why we have this bluish color, because actually it lets the red through it. Picture on the left is that mechanism that moves the filter between in front of the sensors and up onto the carousel assembly. It's a mechanism, things wear, so it's line replaceable. So this is something we can actually take out when the camera is actually installed in the telescope. We have the capability of removing this whole assembly. We have a second unit. We can put the second unit in and then refurbish the first one that needs refurbishment. The picture on the right is actually the filter loader. So the filter loader is what can install or remove a filter from the camera. So this interchanges the color that's inside the camera. That is actually what replaces one of the colors from being in the camera or out of the camera. And once those are installed, magically, voila, it's all done. That's it. Talk's over. Not quite. All right, so this was the beginning of last year when we finished the camera, and then we had to get it to Chile, which everybody knows that all you do is call it FedEx, right? We did not call it FedEx. We chose to go a different path. We designed we took a standard 20-foot shipping container and we modified it to support the camera inside. We have a lot of equipment along with the camera, and we wanted to transport it safely. So we chartered a 747. So that's a 747 loading up at SFO. A little video here of coming in for a landing in Santiago. So early morning landing in Santiago. The pilots were great. They were basically let us have free reign over the whole airplane. We could go wherever we wanted. So it was fun to be in the cockpit when we were landing in Santiago. Picture on the right is that shipping container as it's arriving to the observatory on May 16th. This may have been an ecstatic day for a whole lot of us. This is a huge milestone for us to actually safely get the camera to the observatory. Once it was there, we still had some work to do. So we actually had a few repairs. We had a bunch more testing that needed to be done. Telescope also wasn't ready for us. So the camera on the upper right, that's it sitting inside of the clean room at the Summit facility. So we had to do a few months of work in that clean room at the Summit facility. Once we were done doing that testing, the telescope was ready for us. Took the camera out of the clean room. We put it onto a part of the telescope. That's that lower right picture. The picture on the left is the camera now fully installed. That was March 6th this year. So that's fully installed onto the telescope. I'll point out a couple things here about this image because it can be a little confusing with a bunch of reflections. So the platforms on the left-hand side and the right-hand side, those are just access platforms for working on the camera. They can't stay there when we're doing observations. So they actually retract out of the way. So they're brought in because we needed them there when we were installing the camera. The other thing that's interesting is that when you look here, this is all reflection. This is the second mirror. So everything you see here is a reflection of other things. One of the things that I think is really fun is that this is looking directly down the center of the camera, which is up there. This is that R-band optical filter that's mounted inside the camera. So you're looking at a reflection off the secondary, off the third mirror, down the middle of the camera. That's actually the path of how that image was taken. We had our first on-sky image April 15th, so just a few months ago. Big celebratory moment captured on the right-hand side. There were people watching all over the world. There are literally thousands of people watching this event happen across the world. So seeing that first image come through was a huge celebration. You can see the big party that they had down at the base facility in La Serena. They had fun. They had like beer and pizza. Kevin brought us like non-alcoholic bubbly. And then of course you can see the control room here at SLAC too. So that was a great moment to have this all happen. And so, yeah, it was a rousing success. Nothing ever went wrong. Sure. Let's talk about some things that didn't exactly go the way we had hoped for. 2023 was a really rough year. It was definitely our terrible, horrible, no good, very bad year. We struggled with a few different things. So the first one is we had a flood in our clean room. And I can assure you that getting a panicked call at 4 o'clock in the morning from somebody telling you that we're trying to make an Olympic swimming pool out of our clean room is not how you want to start your day. Luckily for us, there weren't any dramatic negative consequences. We just got lucky. A hose popped off of its connection to the wall. It was dumping 15 gallons a minute of water into our clean room for a couple hours. So a lot of gallons of water in our clean room. So luckily, nothing really bad happened. We just got a nice clean floor out of our clean room. Later in the year, we had a couple of issues with our vacuum system. So I mentioned this cryostat assembly. We have to remove all of the molecules of air. When I say all of the molecules, we have to remove all of the molecules of air. So anything that can leak through any seam causes a problem. So we had a small microscopic leak, not something that you can see. It's not a crack, it's visible. It takes a long time to try to track down where it is. It was especially difficult because where it happened was completely inaccessible. It was very hard to get to. So there's a custom feed through that has like 500 wires going through a feed through between the vacuum and the air, and it's in epoxy. There was a small leak in that epoxy. In order to fix it, eventually we did a bunch of testing. We spent a bunch of time making sure that we were going to do the right thing, and then eventually when we decided to actually fix it, we just spread some epoxy on the surface. It took like 10 seconds. We spent 3 months preparing for it. But the crazy thing is this picture right here, the reason the colors are a little funny is because that's through a fiber optic camera. That's because it was so inaccessible, you could not get to it with a normal camera. Not even like reaching through tight spaces with your phone, we're able to get to that spot. The stick that's applying the epoxy here is about 18 inches long. So you're really in a precariously difficult laying on your stomach, trying to reach through a very tight space to apply this epoxy. Not exactly fun to make that happen. The other vacuum related issue was that our turbopump. So the turbopump is the device that actually sucks all the air out from our cryostat. So the thing spins at 80,000 RPM, so it spins really fast, draws all the air out. And that failed on us, and so we had to replace it. We got lucky in the fact that we were able to do it without having to take apart the entire camera. So the lessons learned is don't put your critical components where you can't reach them. So, the question is, why do we do this? Why do we suffer? Why do we push ourselves on these technical limits? And the obvious answer is fame and fortune. And since we failed spectacularly at that, we do it for the science and we do it for the images. So we're going to take a look at the first of the images that were released six weeks ago. Thank you. So this is part of the Virgo constellation. It's about 56 million light years away. So it's not exactly in our backyard. It's fairly far. It took about 1,100 images stacked on top of one another to create this, what you're seeing here. Now, we mentioned that we have the 6 different colors of optical filters. So each one of those, when the camera takes a picture, it's actually black and white. It's monotone. So we falsely color the image based on what color of filter is in place. And so when you then take a whole bunch of images that are in different colors and you stack them on top of one another, you get a mosaic that includes all of the colors that are occurring from the space. When you look at this particular image, the more blue stuff is closer to us, the red stuff is further away. There's not very many stars in this picture. Some of the stars, like some of the things that are bright, you see these diffraction lines, those are actually stars, but everything else is a galaxy. So there's just a huge number of galaxies in this image. And here is that, approximate size of where a Hubble image might be on this particular image. And you might be saying to yourself, Travis, you told me it was 5,000 times bigger. And both of those things are actually correct, because this is only 2% of an LSST image. It's too much for us to take in. So a single image from the LSST camera is too big for our eyes to see everything. We would need a literal side of a barn here with 400 televisions just to display this one single image, and that's too much for us. So the team made a software tool to allow to be able to move around. Sorry, I'm going to show you how big this particular image we were looking at is. So the team made a particular software called Sky Viewer that allows you to pan around the full image, the full LSST image, and also to zoom in and zoom out. So we're going to look at a video that showcases how that tool allows us to look around the full scale LSST image. That's basically where our first image was. Now it's gonna showcase a little bit of how the images will be tiled across the sky. So that little array there that's moving is a representation of a single image from the LSST camera. And so it's showing in a very rapid sequence how the camera will move across the sky. The images we take are 30 seconds. So we need a lot of time in order to get the light from the very faint objects. So our images are 30-second long. But it takes 30 seconds to capture an image. And then we are able to read out the image and move and start the next image 8 seconds later. So it's every 38 seconds that we're able to actually capture an image. So in that thing, there were like 10 million galaxies in that full image. That's like less than 0.1% of what we expect from the full LSST survey. So it's discovery engine. I think that's the term that people like to use on this project, is that it is the best discovery engine. It's a great discovery engine. So there were like 10 million images on that, 10 million galaxies. A lot of the stuff in there has never been looked at through a telescope. There are a whole lot of things because we're looking at everything, right? So it's everything all at once. And so if we look at another big image, this is another image, a different part of the sky, or you can see a little part of what we had looked at. So this is about 1.5 times the width of a single LSST camera image. And if I show these things, these are the identifiers for everything that has been everything that's in a catalog of astronomical data. There's a lot, but what is more remarkable is that there's a whole lot of stuff in between that doesn't have anything identified. So when we call it a discovery engine, that's what we mean. It really can detect, we're seeing things that have never been really looked at before through a telescope. But it has more tricks. So this thing scans really fast. So we talked about there have been other survey telescopes. There's been several other survey telescopes. This is significantly faster, so 10 to 100 times faster than any previous one. So this is what we've been looking at. Would have instead of taking a few nights, could take up to a year for one of those comparable telescopes. And we take a lot of really fast images. So we talk about this digital color movie, right? I mentioned that at the beginning. It's a time-lapse movie. And so there are things that happen in the transient objects as well. So we'll take a look at one of these transient objects. So it's that same image we're just looking at. We're going to zoom into a little corner down here and look at this particular area. So we have this nice, beautiful spiral galaxy, and we've taken a lot of images, right? Just like we had before, a whole bunch of images stacked on top of one another in order to get all the color and the depth that we see. And if we look at this one, it's the same one, but you see these little colored streaks. These are asteroids. So you can see that there are colors. There's like a streak that has a red, a green, and a blue, and maybe some other ones too. And that's because I mentioned each of our images, we falsely color based on which color filter is in place when we take the image. So we take an image, change the filter to a different color, take another image. In that time, these asteroids have moved a little bit, and then we're capturing it again, right? So you're actually seeing these streaks. Software takes it out automatically. But we can actually look at them if we want to look at them. So if we want to look at them in detail and actually monitor asteroids, which is a whole community of scientists who want to do just that. So we'll watch another video that showcases the power of this observatory to see these transient objects. So you can see this black and white image. That is what a raw image from the LSST camera looks like. So each one of these things that you're seeing is a unique asteroid that has been first-time discovery. There's a little counter at the bottom here for the nights of observation and how many asteroids. These are new asteroid discoveries. I don't know, there's a asteroid belt that exists between Mars and Jupiter. That's where these predominantly are taken. There's a theoretical band, and then you can see what we have discovered. That was in the first 7 days. That was the very end of April and very beginning of May. It's about 10 hours of observation time to discover over 2,000 asteroids, new asteroids. Some of them were near Earth objects, but they're not going to hit us, so don't have to worry. There's about 1 million known asteroids right now. We expect that just over 5 million in the next couple of years. I was trying to find what the current number is, but I didn't get that. So yeah, there's a lot more about this observatory and the images. You can go to rubinobservatory.org. There's a little QR code for this sky viewer. That was the cool little app that lets you pan and zoom across all these images. So you actually can go and you can download the app yourself, so you can take a look at. There's a whole bunch of images available on the website. So I just want to give quick thanks. Our DOE Office of Science, the people who funded this project. So thanks for making sure that they believed in us. SLAC senior management team for supporting us. And then we've got like this incredible team of scientists and engineers that over the years have been working to put this thing together really diligently and making sure that this thing works as it's supposed to. This includes people here at SLAC as well as in Chile. We have some scientists who are very busy, like literally right now at the observatory, working on this. And there's the image from when the camera arrived in Chile. This is one of my fun favorite pictures, showing a select group of people inside the clean room when the camera was just completed. And I think this is one of my favorite ones that shows literally every single person who happened to be at the observatory the day before the camera was installed onto the telescope. So we took 2 days to install the camera on the telescope. It takes everybody. There's everybody from the director of the entire project to the janitor of the observatory, and it takes everyone to make this thing happen. And then I need to give thanks to my family, because it's a lot of sacrifice, and it's also a lot of sacrifice of my family too. And that's true for everybody involved on the project. And lastly, thank you. It's your taxpayers' dollars that are funding this project. I hope you find that it's well used money, and also like I appreciate your enthusiasm for this project, and I hope you're excited about it and you want to tell other people about keeping this funding in place. So thank you.
Well, Travis, thank you very, very much. We have time for questions. So what we ask is the following. There are people who are going to go up and down the aisles with microphones. This session is being recorded, so get your question on the recording. Raise your hand and I'll call on you. When you get the microphone, then start your question and Travis will answer it. So who'd like to go first? Way in the back there.
Hello, thanks for the presentation. Just curious, what was the design choice to sort of get the lens attached first to the assembly before putting in the shutter and putting in the stuff in between, as opposed to just going end to end?
I mean, that's a good question. The reason for putting the lens assembly on first is we have to be able to replace the shutter and the auto changer or the filter exchange system regardless of whether the lens is in place. So that's something we had to figure out anyway. And the other part is installing that lens assembly was one of the more tricky parts, and we didn't want to have the other stuff in the way when we did that. So that was the rationale for going that route. So installing it first.
Okay, over here.
Thank you so much. Like, it's a very great presentation. I have like the questions. So why we choose to build the camera in Rubin, that observatory, since you probably have like the multiple choice, right? And then you also mentioned that the size of the camera is actually restricted by the tunnel. So why you choose that location? So that's my question.
Yeah. Okay. So a little bit of a couple part question there. So the camera is not limited by the tunnel. That was the mirror that was limited by the tunnel. But as far as the location, Chile has very dry skies, very low light pollution. It's also probably one of the bigger factors is that the property that exists has a few other telescopes on it, and it's property that's owned by the organization that manages the Rubin Observatory. So the property already exists. It already has all the facilities, right? Power, water, all that kind of stuff. There are already other telescopes up there. I think those, combined with the fact that Chile is just a very good place. The northern Chile is a good place for doing observations. I hope I answered the question.
Who's next? Please.
Yeah, thanks for the talk. I was just curious.
Yeah, maybe it is.
Let's say if you had a bigger tunnel and like 20% more budget, what's like one more thing that was, I really want this, but we can't have it?
Infinite budget. Does that exist? I haven't seen that. Yeah, I mean, I think you scale up everything. Maybe. I mean, the camera's already kind of pushing the limit for how big you could go. I don't know that we'd actually be able to make a bigger lens for the camera. It's already, it was already difficult enough as is. Obviously, the mirror, if you had a bigger mirror, you could collect more light. Maybe you could get away with, a bigger mirror and not have a bigger camera. I think that would be pretty tough. I'm not sure if there's any specific thing that I would say that would be what we'd want to spend extra money on. I think if we had 50% more budget, we would have built 2 of them. So we would have one in the northern hemisphere and one in the southern hemisphere. And that probably would be the way, because you could use some, efficiencies of doing 2 instead of just 1. So maybe that would be the thing that we would get out of extra money.
Yes, please.
Thanks for the talk. It was really interesting. A question on the maintenance cycle, because I'm assuming this thing is not going to run forever without any maintenance. Do you do daily maintenance? Is there like a 10,000 hour check engine light that goes on? What's the cadence that you plan to spend on maintenance?
There is in fact a check engine light that comes on. No, I'm just kidding. We do have, we're setting up all the maintenance cycle right now. We are actually planning our very first maintenance window in October. So we're actually going to do the very first maintenance on both the camera as well as the rest of the observatory in October. You can talk to the guy in front of you if you'd like about the details. So that's coming up. And we do actually have software where we put in the different trigger mechanisms for maintenance. Some of them might be time-based, some might be event-based, and some are usage-based. So those different trigger mechanisms, the software will actually say, okay, it's time to do this maintenance. It creates a ticket for us, Jira ticket, and we'll use that to then schedule the work to get done. Sure.
Sir.
I was wondering if the design of this telescope brings anything particular to the study of dark matter, dark energy, the spatial field of view or the timescales that it brings.
Yeah, it does. I mean, I'm not going to get into too much of it, but I mean, it's really the how the structure of the universe is changing. So monitoring the time domain changing of the structure of the universe is where we can get some of those things. Weak lensing is one of the real aspects for the dark energy that's going to be one of the tools that we're looking at. And there's a whole group of people that are looking specifically at various weak lensing aspects.
Maybe I should just comment on this.
Yeah,
weak lensing is basically the distortion of background objects due to foreground objects. And that distortion takes place by mass changing the trajectories of light. So one of the goals of this project is to measure the shapes of the galaxies. and to try and determine statistically how their shapes are distorted from the original shape by the passage of light in front of it by the foreground objects. And that basically maps the dark matter in the visible universe. So we're going to learn a lot about where dark matter is and what its regularities are. The fact that you can take a movie, which basically gives the evolution in time, is also going to tell us about the expansion of the universe. We'll have talks on all these things when the data is analyzed, but for the moment, it's just beautiful. Okay. I think, sir, you had the next question. Why don't I just give you?
Thank you for the wonderful presentation.
Sure.
I was curious if AI played a role in any of the projects to date or in the future.
Not so much in the design and construction, but yeah, absolutely in the future. It's definitely a big part of it. In fact, actually, some of the tools, if you go to the website, the Rubin Observatory, there are some educational tools. There's some games that you can play. Actually, the games are actually helping to develop the AI models. So yes, we need a lot in order to decipher all of this data. It's too much, right? There's just too much data for individual people to sort through. Like we can't. We don't have enough people on the planet. And so we need the use of AI tools to help us with that. So yeah, that's absolutely going to be a big part of sorting through all the data.
So quick question about the data. Let's say I'm interested in a variable star somewhere. Is it possible for me to get LSST imagery data, or is that all through NSF and PIs? And
yeah, so Rubin is really unique in how it operates. Instead of the traditional way of observatories is that a scientist will apply for some time, take a bunch of pictures, and they keep those pictures themselves, right? Rubin is doing things a little bit different. We are doing all the pictures, and then we are saying, here's all the data, come and find it. So there is a way for citizen scientists to get involved. So you, as somebody who's not even involved with a particular collaboration, could get involved. And there are some things that happen, quickly, right? We talked about the asteroids. There's also, some comets or supernova, things that happen relatively fast. There are alerts that will come out. So the camera shutter closes, the data takes 10 seconds. It's here at SLAC. It gets analyzed, gets processed, and then anything that's different from that image that just is captured to what already existed, it will do the difference imaging analysis, flag everything that's different. We expect like 10,000 different things in every image. And then if you are someone who's interested in one particular thing, sorry, I forgot what you even had mentioned, but
let's say it's T corona borealis.
Yeah. So if you're interested in that one particular phenomena, you can basically sign up, and you will get an alert saying, "Hey, this is happening right now," and you can take your backyard telescope or your big telescope that you're running for some other group and look at that thing happening in real time.
Okay. And another thing, you mentioned cryostat. My cooled camera has a Peltier cooler, right, for the sensor.
Okay.
And I was just wondering, what do you mean by cryostat exactly? What's the cooling technology?
The cooling technology is a custom mixed refrigerant. So it's basically a refrigerator, but it's a really custom mixture of refrigerant gases. So it's an evaporative style cooling, just like in a refrigerator. So it has an offline compressor system. We pipe in some gas, it expands. We get the liquid back out. That system is, we have to remove a fair amount of heat. The CCDs themselves, we have a little over 100 watts, about 150 watts of power that we have to remove. The electronics that support them is more like 1,200 watts. So all of that stuff has to be removed. And we have two different independent refrigeration systems because those things operate at different temperatures. So we go on and on about thermal control, thermal management. There's a whole bunch of thermal management zones inside the camera.
Okay, let's just take a couple more questions, please.
Yes, thank you for the presentation.
Sure.
So this is called the camera, but it sounds like it's doing a lot that normal cameras don't do at all, such as the cooling and obviously the electronics of just moving that thing around have to be like tremendous. In what ways is this not at all like what we think of when people usually use the word camera?
Yeah, you're right. I mean, we do call it a camera. I actually sometimes use the caveat that it's a camera, but it's actually a really complicated scientific instrument. So it takes images, it does capture images. So in that way, it is a camera, but it's not a camera because, you know, they're all out of focus, right? We need optics from the telescope, for instance. So when I show you the picture of just the camera by itself, that will not take a pretty picture, it'll just be a blur of nothing, unless we have a pinhole to restrict the amount of light that comes in.
Like how big an iPhone would I need to have the computers that process all that data?
So, I mean, there's a couple things, right? So, you know, this is 48 megapixels, right? So it's a lot of megapixels. So I need, somebody do the math for me, you know, 80 or whatever it is, 80 of those things stuck together to make the same number of megapixels. But it's not just about the pixels, it's also about the precision, right? So we're trying to do science and not just take pretty pictures. So what that means is like all the noise, right? I mentioned the electrical noise. We have to reduce all that. So that's really unique about this camera. And the other thing is the location, the spacing, how well we control how well we monitor the signal level on each of those pixels. So all of those things that really come into play when we're using this for science. We really need all of that to be really precise.
Take two more questions, sir, and the fellow in front.
Hi. After the long trip from SLAC here to Chile, there must have been some adjustments you had to make. Some things must have got knocked out of shape just slightly, maybe the mirror or maybe the individual pads of photosensors. Now, how did you go ahead and repair those?
I will try to convince you that nothing actually happened. So I mean, that's one of the reasons why we wanted to test it after it arrived, so that we could prove that nothing actually changed in the process of shipping it between here and the mountaintop in Chile. The other thing is we spent a lot of time and a lot of money preparing the shipping for the camera. We actually did a complete dry run, right? So we actually put a big thing that looks just like the camera. It's made of steel, and we shipped it to Chile and back. And we drove it around the Bay Area on a truck. In fact, we put it in the truck, and we told the guy to find the biggest potholes he could find. Literally, go on Highway 101 and find the big potholes, because we wanted to test out to make sure that our isolation wasn't going to provide any shock load into the camera. We have monitoring. We logged all the shock load and the temperatures and the pressures throughout the entire process of shipping. We checked all that data upon arriving. There was nothing that gave us any concern when we opened up the box.
Okay, so please hand the microphone down to the fellow in front of you.
Oh.
Thank you for the talk. How do you calibrate the individual CCD pixels? I mean, a CCD has variable pixels of black level, gain. So how do you calibrate these gigabytes of pixels?
Carefully. Yeah, there's a lot of testing that went into that. So gain, we had iron 55 sources that provided counts, a fixed number of counts on the sensors, and then you could see the variation across all of the channels of the CCD, because each CCD actually has many channels that it reads out, right? There's 16 channels, and so you monitor all of those channels, and then you create a bias level so that they're all at the same bias to start with. So that's one of the aspects I think you were just asking about. There was a lot more testing that went into it. So we actually put this thing in a dark box with very known frequency or known wavelength light sources that could points at very known locations. So that's one of the other tools that we use for for calibrating the CCDs. I'm sure we go on to that in a little bit. You want to add? Sure. Yeah. Yeah. That was just for camera sensors. Now that the camera is a part of the observatory and not an individual thing, there's a whole different set of of calibration tools. So the calibration screen that Kevin just mentioned, it's a humongous screen that gives us a very uniform, flat, uniform light on a screen that we can use to calibrate the CCDs.
Okay, well, Travis, thank you very much.
Sorry.
Okay, and thank you all for coming. I hope you've been entertained and informed. We'll have the next one of these toward the end of September. Many of you are on our mailing list, but if you're not, go to the, just Google the SLAC Public Lectures. There'll be a way to sign up for our mailing list to get all the announcements of these events. The people here like to clear the auditorium, but you can come outside into the lobby, and very soon Travis will be out there. If you want to talk privately or ask more questions, we can keep going. So thank you all very much for coming.